So today we're going to be talking about computing at scale in our panel. And I want to say a little bit about what we mean by computing at scale. So computing at scale includes high performance computing, but also cloud computing. And if we think about the technology that has contributed to these areas, including software, hardware, including architecture, circuitry, distributed systems, programming languages, advances across the board in research in these technical areas have contributed to an enormous increase in our availability of computing cycles for many, many different purposes. Let me share one example of that from my own personal perspective. So I was a researcher at Microsoft Research, but in 1992, I was looking at the issue of program synthesis and creating programs just by expressing what you want instead of writing code was just a vision at that time. Now, in about 2010, I got the fortune to work with a colleague, Sumit Gawani, and we developed a technique which is now available in Microsoft Excel, which is called flash fill, and it allows users of Excel to do string manipulation by example. So instead of having to write the code themselves, users who didn't know how to write code could transform strings just by showing examples. And that was in the early 2010s. Now, 10 years later, we have a new technology on the horizon. And we've seen multiple instances of this now in papers that have been released in the last year. Specifically, computers now are able to take program descriptions, things like a programming contest description, and create a solution to that description entirely autonomously. So this is an enormous advance in the capabilities of computers, and they're all powered by computing at scale, which we're going to talk about today. Now, I'm joined by 4 very distinguished panelists, and I won't go into a lot of detail about their biographies, but I encourage you to look at the bios on the website because they have made enormous contributions to this field, and we're very lucky to have them here today. But I'll introduce them briefly. We have Luis Andre Barroso, who is a Google Fellow leading the Office of Cross-Google Engineering, from where he coordinates technical initiatives that span all Google products. Ian Foster is a senior scientist and distinguished fellow and director of the Data Science and Learning Division at Argonne National Laboratory and the Arthur Holly Compton Distinguished Service Professor of Computer Science at the University of Chicago. Timothy N. Pinkston is a George Flegger Chaired Professor of Electrical and Computer Engineering and Vice Dean for Faculty Affairs in USC's Viterbi School of Engineering. And finally, Catherine Yellick is the Robert S. Pepper Distinguished Professor of Electrical Engineering and Computer Sciences and the Vice Chancellor for Research at UC Berkeley. She's also a senior faculty scientist at Lawrence Berkeley National Laboratory. So we're very lucky to have these distinguished panelists. And the way we're going to structure our conversation today is I'm going to be asking 4 questions to the panelists, and we're going to discuss those questions, looking backward at the contributions that NITRD has made, I'm sorry, I get the pronunciation right, NITRD has made, and also looking forward to try to understand, as has already been mentioned, where this technology is going and how it's affecting society. So I'm going to start with the questions. We're going to then go to the audience, and we'll entertain questions from the audience as well. All right, so I'll start. And this question will go, Luis, we'll be asking you to start our conversation here. The question is, in what ways have NITRD investments accelerated advances in computing at scale, and what made those investments successful?
Thank you, Ben. Real pleasure to be with you all here today. You know, I confess I didn't know what NITRD was when I was first invited to be here a few years ago. So it's been really illuminating to look at the role that NITRD has had across the research agencies. And I did a little bit of research just looking into our own company and in what ways this program has benefited advances that we are able to bring to the public today. And it's interesting, Dr. Nelson mentioned digital libraries in her introduction because even though we're here to talk about high performance computing in many ways, Google started from a digital libraries investment made at Stanford. Professor Terry Winograd was the advisor of Google founders and had a grant to work on digital libraries. and everything sort of stemmed in some way from that investment. So I thought I could not start my answer to that question without mentioning this specifically. More to the topic of high-performance computing, we at the infrastructure we've been building at Google over the years has clear lineages across research efforts in industry and academia. I'll mention just one in academia, which is the effort at Berkeley on networks of workstations, which is one of many efforts that was trying to look at how can we make distributed systems incredibly effective as a power to rival the supercomputers of the day. And so much of the DNA of Google's from the very early days of being very frugal and buying relatively inexpensive computing gear and putting them together in clever ways, I think is definitely a result of some of that investment. I'll mention a couple just very briefly. Years later, software-defined networking has been really a pivotal set of innovations that we have benefited on. Today, the kinds of things you can do in terms of traffic management and security would not be possible with networking the way it was before. And then finally, clearly AI and investments in AI are behind so much of what we do today. And AI was not invented at Google at all. But we benefited from so much of this investment. I'll mention just one again. Andrew Ng from Stanford came and started Google Brain with Jeff Dean years back. And of course, his research benefited from the funding from agencies that are coordinated by the NITRD program.
Anybody else want to offer some thoughts?
Well, I can say something. So as I was preparing for this meeting, I was thinking back to over my career, and so I started at Argonne in the early 90s, and I was very excited at that time to have access to a 6-processor computer as part of a thing called the Advanced Computing Research Facility, which was established by a young fellow back then called Jack Dongarra, who interestingly has just won the Turing Award, the Nobel Prize for Computing, for his work on high-performance computing. So it's very timely, actually, that this award happened this year, given this 30th anniversary. Founded by also with another colleague, distinguished colleague, Rusty Lusk, who sadly just passed away. But and since then, the computers that we've got to work with have increased in power by roughly 1 billion times, and the number of processors by probably 1 million, depending how you count. And most of those innovations were first explored in university settings or national labs with support from the NITRD, have I got it right? NITRD program. And so bigger and faster is great, but what is it enabled? Well, the deep learning revolution, weather forecasts that can look out 10 days and be remarkably accurate, new drug designs, the COVID response, all of these things, I think it's clear they've been made possible by these investments from the federal government.
Anybody else?
Maybe I could just add a couple of things. Just, especially for the younger people here in the audience, it may not be clear that back when NITRD was started, that parallel computing was sort of a niche research area, right? There were a few crazy people like Ian and myself and others who were working in that area, but it really wasn't until multi-core, with end of Dennard scaling came about that everybody else started worrying about parallel computing. And even in the cloud early on, it was mostly for more independent jobs, and now I think there's huge machine learning models and things that are trained on taking advantage of parallelism. So just that sort of early investment in NITRD, and I think not all of those people, it's also about the training, the expertise that went out into places like Microsoft, Google, Amazon, Facebook, et cetera, and are now helping to figure out how you take advantage of parallelism for a lot of different application problems. The other area, though, that we haven't touched on, and I'll go back to the Google search example, the original sort of algorithm there, and that's the applied math investments and kind of investments in related research in statistics as well as applied math, and how, my understanding of that, of the founders also went to consult with one of the applied math faculty at Stanford to say, well, how would I solve this singular value problem? And got a good idea on that. So those investments also are really important in that NITRD has made in terms of fueling, I think, much of what we do today.
Thanks. All right.
So let me just say something about maybe the mechanism for some of these investments being made. I had the fortune of being at NSF for a few years back in 2008, 2006, 7, and 8. And was helped to engage with the community on what kind of investments should be made, and so at that time multi-cores were nascent, and we were able to put together a funding initiative for multi-core design and architectures and the design automation for that, and the Expeditions in Computing program started at that time. And the idea there, this was under Jeanette Wing when she was the SCI's AD, it was the question of how can we make large-scale investments to really move the needle in computing more broadly. Of course, what benefited from that is, of course, high-performance computing and cloud computing and others. But through that, we were able to make the initial awards made that helped to significantly move the needle in software-defined radios and in computational sustainability, which is a field within computer engineering, within computing. That was one of the awards that we see the second award in molecular programming, designing how do we program molecules to do computing, and that also won a second Expedition Award. And so the mechanism through NSF and other agencies for looking at where can such investments really move the needle and change the landscape, I think we benefited from that through NSF and other funding agencies.
Thanks. Yeah, I have experience with the Expeditions in Computing because there was one funded in program verification, and it's close to home with my research interests. And I think that, like many of these investments, it's a very long-term prospect. But on the other hand, and I'm sure we'll hear from the security panel later, having that verification is going to be very, very valuable now and going forward. All right, so we'll move on. The next question, which we'll have Kathy start our discussion. What are important societal outcomes that NITRD investments in computing at scale have enabled? And where are opportunities for even greater impact?
Well, it's a great question, and it's hard to capture it. I think we've heard already some of the examples from the previous speakers today, but I'll go back also to the sort of early days of NITRD and say I think HPC, or high-end computing, was really synonymous with simulation, modeling and simulation. And so I think some of the big breakthroughs have been in that simulation area. So things like the Intergovernmental Panel on Climate Change, IPCC, and the understanding of climate change kind of in advance of what we're seeing today through observation has really been fueled by high-end computing and the ability to simulate and make predictions, both for climate change long-term and also weather, which we see kind of in terms of our ability to predict what's going to happen in the short term. I think the other then examples of that include chemistry, where there's been a Nobel Prize in computational chemistry, and in material science, where we also use massive amounts of computing to screen through new materials for various energy applications, as well as using it for drug discovery, things like therapeutics for COVID or for cancer treatments. and things like that. So secondly then is though looking at data analysis and the fact that the instruments that we use and the devices we have even in our homes or in our hands are so powerful today that it takes a lot of computing in order to analyze that data. And so things like the sequencing of the human genome, that was a huge computational undertaking in addition to the actual sequencing task. The overall cost of that, though, was about $300 million. So you could say, well, we needed to do that computation once, but how many times we're going to be able to afford that? But of course, now the cost of sequencing is under $1,000, and we're also sequencing massive data sets. One of the projects I'm working on now is looking at environmental samples where we're getting, say, 10 terabytes of data from the soil and then sequencing that. And that's also turns into a huge computational problem that we're planning to run on exascale machines. So those are some of the things that we've seen, I think, in the data analysis side of things. And then last, of course, machine learning and whether you want to call it AI, deep learning, but specifically the deep learning algorithms, which really became so successful not because of a recent algorithmic innovation, but because of the size of the data sets and the speed of the computers. And, by the way, the understanding of how you can take those algorithms and turn it into something we all love in this community, dense matrix multiply, that runs about as fast as anything will on any of the hardware. And so those kinds of innovations, I think, and that have led to, and we'll hear more about video conferencing and how that's, of course, really saved us in some sense in this COVID pandemic to be able to continue with a lot of our research collaborations, our teaching and business operations, but also things like the closed captioning that shows up automatically. It's not perfect, but 20 years ago, we would not have had that at all. And it's a great aid to many of us who don't always hear everything that's going on. So those are some of the things that I think have affected all of us.
Great, thank you. Other thoughts?
I'd like to mention a couple of things. So we've talked a lot about innovation, which of course is so important. But the program has also had a really important role in two related areas. One is creating facilities, computing facilities, data facilities, networks that have allowed scientists to work on these challenging problems that we've been talking about. The fact that the supercomputer centers, the national labs, and others have established and run massive computers that are now approaching exaflops scale is a really important development. And then something else that I think Tim sort of hinted at, the fact that this program has allowed the creation and sustained the creation of interdisciplinary teams. So computer scientists plus computational scientists, applied mathematicians, and discipline scientists who've been able to work together over multiple years in programs like the Expeditions programs, the DOE SIDAC program, and others, I think has been so important.
The interdisciplinary aspects of it, I think, are incredibly powerful. And we're seeing this today as we begin to democratize the power of AI in particular. IT is behind just everything in society these days, but to some extent has been very much inaccessible to specialists in biology or in ecology or material sciences who happen not to be trained as programmers. And I think that the ability that we have these days to bridge this gap and give tools to these professionals that have extremely irreplaceable domain knowledge and allow them to apply really, really high-end computing technology to what they do with less and less friction over time, I think it's incredibly inspiring to me.
Ditto.
Yeah, I'm curious now, Kathy, I want to know more about your sequencing of the terabytes of data in the soil. I was involved in a project at Microsoft looking at the blood in a mosquito to think about what kinds of metagenomics you could discover about the animals that mosquito had drunk the blood of. And
yeah, I'll just say that, well, first of all, I think even going back to the human genome, what is really fascinating to me is that, although that first, that it was many years ago when in the original construction of the human genome, the sequencing of it, but it was really just completed this year in 2022 in terms of having a really complete completely filled in sequence, because parts of it had so much repetition that it was really hard to reconstruct that from the fragments that come out of the sequencers. And that's the problem with metagenomes. When you collect something like in the blood and you've got all these different microbes living in there, viruses and bacteria and who knows what, hopefully not too much in your blood, but anyway, but also in something like a scoop of soil, when it gets sequenced, they're all mixed together. So you may have 10,000 species all mixed, and you throw that into a sequencer, and what comes out, you need to take all these fragments and put them together into 10,000 different genomes. So that's why the computational problem is also very hard.
And it reminds me of the advances in understanding the gut biome too, because fundamentally it's like there's a lot going on there, and until you actually can do the analysis, it's very hard to understand it. Okay, so our next question, which I'll have Timothy lead off the discussion on, is given how hardware, applications, cloud infrastructure, and computing at scale, including cost and trade-offs, have rapidly changed in the last 5 years, and there have been a lot of changes, even in the last 5 years. I think this is the thing that I've noticed, is that we seem to be in an accelerating period where things are actually happening faster and faster. So given that, I think the question is, should NITRD investments in computing at scale change? And if so, how?
Good question. Over the last few decades since the inception of NITRD, we've seen a remarkable evolution and burgeoning expansion of computing in various form factors, functionalities, capabilities, performance, comprising a vast cross-scale computing ecosystem which has benefited humanity, and it continues to expand. So the question is, how do we continue that? We must make investments that will sustain this remarkable acceleration and expansion. The evolution of computing certainly, no doubt, has been impacted by Moore's law, which defined transistor scaling. Despite the slowing down of Moore's law, I think perhaps a more significant outcome from Moore's law, a more significant impact and influence is on our expectations for continued increase in scaling of computing capability, a doubling every couple of years. Whether or not Moore's law, actually we see the ending of Moore's law soon in terms of transistor scaling. What I think Moore's law, we can view Moore's law more broadly in terms of setting the goalposts, defining and setting expectations, providing an aspirational target for scaling of computing that goes well beyond the mere rate of increase in the number of transistors integrated on a chip. It's transcending in some ways. It's the idea of Moore's law in this broader context promotes this notion of exponential improvement and expansion and advancement of computing along a number of different dimensions. Certainly in terms of overall functionality, capability, and performance, but also in terms of reduced form factor and reduced costs. And also in terms of the growth and robustness of applications benefiting from and running on computers, in terms of increased security, reliability, and trustworthiness of computing, and in many other ways imaginable, including energy efficiency and sustainability, all at scale. So how can we continue keeping pace that we've seen amid looming technology limitations and constraints? Well, so we need to make the proper NITRD investments. So let me also remark that we've seen in this exponential computing gains, we've also seen this evolution in the underlying semiconductor technology. And that's from very unreliable and power-consuming switching technology devices at the device level to the more reliable and less power-consuming CMOS-based technologies. But we are seeing these days a slowdown, let's say, of CMOS technology. We're realizing a slowdown in the physical scaling of CMOS technology and increased power constraints that are exacerbated by Dennard scaling. So now we're at a place where in order to have more energy efficient and sustainable computing at scale, it's the right time to make new and important investments from NITRD in perhaps potentially high risk but high payoff technologies. Let's say for logic and memory devices, technologies, and non-classical computing paradigms. But with this comes, as they may operate on different physical principles than CMOS technology, there may be unique constraints or trade-offs of these more novel, exotic technologies, which we would hope can be addressed by technology-specific abstractions, architectures, compilers, software, algorithms, runtime systems, and of course, design automation tools, so that we can be able to mitigate those perhaps technology-specific constraints and obstacles and challenges, but yet get the yield of the potential performance gains that we can get from this. So an example of this would be NITRD's recent investments in quantum, nascent quantum computing, and within reach superconductive electronic computing approaches that utilize Josephson junctions at the underlying semiconductor switching technology, which promises to have orders of magnitude lower energy and power consumption per high-speed operation relative to CMOS. Again, whatever constraints there might be and new trade-offs there may be with these new technologies, we would hope and expect that the entire computing stack investments in the entire computing stack could help to mitigate those and allow for the much higher energy performance efficiency that we would expect to be realized from such investments. And so investments like that, investments in neuromorphic computing and coherent icing machines and in biological processes that might use cells as a basic computing element, and other such non-conventional, non-classical computing paradigms, I think are well worth the investment of NITRD in the future.
Great, thanks. Yeah, I had the fortune to work on or worked with a colleague that did investments in DNA storage and using DNA specifically for storage. And so that's a good example of kind of non-traditional computing. Thanks for sharing that. Others, do you have thoughts about where we are? Yeah.
Well, I just wanted to emphasize that I think, if you look at the Turing Award, I guess, paper and presentation from David Patterson and John Hennessy, it's on the golden age of computer architecture, right? Because, I think there again, if you look back, there was a time when it seemed like there wasn't much room for academic research in computer architecture because so much of it was driven by, the industry and a small number of computer architectures. And now there's just this huge growth in specialized processors for deep learning especially. I'm worried that we're all designing deep learning processors. I hope we look at some other things. And I think that's a very important thing for NITRD to think about investing in, which is I think the cloud providers are going to be, and do already, Google and others, providing us with really unique sorts of hardware platforms and architectures for things that are, in which there's a broad market interest, and there's also maybe a scientific research interest in using them for things like deep learning. But there are also a lot of problems in which they may or may not fit on those processors. And I think NITRD needs to invest in the broader spectrum of things. What are specialized processors that we might need for edge devices in telescopes or in space where they have to have special operating characteristics, or for genomics applications where we're dealing with 2-bit characters of data that we're analyzing. So those things may or may not cross over into the commercial sort of area of interest in terms of architectural innovations. But there's a huge interest right now in and a lot of work going on in architecture is one of the ways of getting more computing performance. I also just wanted to talk a little bit about the business model, right? So there's what I think of as cloud computing, at least public cloud computing, is really a business model that says I don't buy a piece of hardware and buy a building to put it in and a power plant to put next to it and everything. I buy the computing as I need it. On the other hand, if I know what I want and I have a particular computing need for, let's say, whether it's a security application or a science application or something else, I may want to really control the kind of hardware that's going in there if it's going to be specialized to exactly the workload that I want, and I may be able to run that. So I think that sometimes people get into the cloud versus HPC center. I think it's a yes and, right? I mean, we absolutely, we're trying, NSF is innovating in a project I'm involved with called Cloud Bank to make it easier for people to get access to computing in commercial clouds, which I think is absolutely wonderful. And I think there are also times when you should have access to machines that are really built for a scientific kind of problem that you're working on. And I don't want to leave out the networking, because as the data sources have increased in performance and the computing, as we look at centralized and edge, some amount of computing happening at the edge, it's clear though that we need to move data around in order to compute on it efficiently, and also to have resilience and things like that in our infrastructure. And I didn't even appreciate this until I was at Lawrence Berkeley National Lab and was overseeing ESNet, and that's DOE's network, and of course Internet 2 for that NSF funds, that these are networks built for a community of people, and that it's not just, there's a feeling that the network is just there. I just walk into my hotel room and suddenly the network is there, but somebody pays for it and somebody has to maintain it and manage it and ensure that if you're going to send huge data sets from, let's say, Argonne to Berkeley to run on our supercomputers, or the other way to run on their supercomputers, that you need to have a really dedicated high-speed network.
Thanks.
I was going to pick up briefly on the accelerator aspects of it and the idea of the opportunity that's ahead of us in computer architecture. One of the things that we certainly need to do better is just design tools for silicon, right? I mean, I haven't designed silicon with my own two hands for over 20 years now. And I look over the shoulder of my colleagues at Google who are designing accelerators, not for machine learning only, but for things like video and YouTube encoding and video conferencing. And goodness gracious, we have not made significant progress there. And if we are going to take advantage of this challenge by Hennessy and Patterson, we need to have better tooling to expedite the design process.
That's great. Ian, do you want to offer any comments?
I think we've covered lots of things here, so let's move on.
Sure,
Yeah.
please.
So let me just say that, just to put it simply, in my view, NITRD, in terms of investments to be made, NITRD should make visionary, aggressive, time-critical potentially transformative, possibly high risk, high payoff investments up and down across the computing stack. From the underlying semiconductor device, or perhaps non-semiconductor-based device-based switching technology, all the way up through the computing stack at the higher levels. And the interconnections, the cross things that cross play as well, including design automation tools that enable it, that may be specific, technology specific, may be application domain specific, if there's a high payoff for it. But particularly for some of these non-traditional, classical design computing paradigms. So such investments, I think, should be made strategically to keep the U.S. To maintain its preeminence as a technological world leader across computing, across the entire computing ecosystem, but certainly including computing at scale for the benefit of all humanity, and so that we can continue to improve people's lives and society more generally.
Yeah, that's so important, right? So the computers of 50 years' time, we have no idea what they'll look like. They won't be anything like what we have today, just as today is not like what we had 50 years ago. And that's not just the computers, but how people use them, the problem-solving methods. And in a way, a danger of high computing being so successful is there's a tendency to focus on the near term, because we've got to apply what we have as best we can. But we've also got to be investing in the things that we don't know about, the things that will lay the groundwork for what we'll have in 30 years' time or 50 years' time.
Yeah, it sounds like a slight variation of the innovator's dilemma, where you have a great successful technology, and it's hard to think of the things that will come after it. And that leads us to the final question, which is, looking forward, how should NITRD investments in computing at scale take into account the increasing need to understand and implement the socially responsible application of computing technology? So Ian, we want to start us off with that one?
Well, it's a huge question. So I'm going to take one angle on it, and I'm sure others will take some other complementary angles. So, I think some exciting things that have happened over the last 3 decades is computer simulation, big data analysis, and increasingly also machine learning, AI methods have gone from niche ideas to mainstream problem-solving methods. So if we want to understand how to respond to a new pandemic, we're going to be harnessing all those capabilities and the associated teaming capabilities, using the best technologies we have today. At the same time, these capabilities have been developed, but they're not well distributed. They're stovepiped in their applications. Certainly not everyone has access to them. Putting it a different way, the US and the world certainly don't harness all the intellectual capabilities of everyone that could be contributing to solving the problems that we face going forward. So I think a major challenge for NITRD and the US and the world is to think, how do we create if you like, a problem-solving infrastructure, an ecosystem of data and computing and people that will allow us to harness all of the intellectual capabilities of our people and apply those capabilities to the most important problems that face us. So, of course, we have, in some ways, the greatly democratizing power now of cloud computing available to us, but that also has its limitations. Its development is driven by commercial forces. Not all of its capabilities are available to everyone. So we need to think about how we would perhaps, as a country, create an infrastructure that will allow anyone with a good idea, not anyone with the right good idea can pursue it, that they can pull together the data resources that they need to ask questions, create the simulations that they'll use to explore alternatives. They can call upon AI and machine learning methods to accelerate the way they approach them. So, what would such an infrastructure look like? I don't think we know, but a few of us have coined the term national discovery cloud for this sort of all-encompassing, democratizing linkage of our different resources. So I think thinking how to create that will probably be some sort of public-private partnership is going to be a big challenge going forward. And then we need to think hard also about what problems we apply that to. NITRD has been so successful at pulling together interdisciplinary teams to address challenging problems of the past, of the present, I guess the past and the present. Many of these problems, of course, continue into the future, things like climate change, environmental disasters, clean energy technologies, pandemic response, new healthcare approaches. So we need to keep thinking what are the most important problems that we should address and for which we would want to create this all-encompassing infrastructure. I think there's also much work to be done in terms of broadening the set of perspectives that are brought to bear in addressing some of these questions. For example, climate change. Well, many people are building powerful climate models that are increasingly good at projecting what's going to happen in different parts of the world, for different parts of the economy, different parts of various human systems. But it's only fairly recently that people have started to think, well, how do those impacts vary according to the socioeconomic situations of the people that are being impacted? So environmental justice is a growing concern, and that's something that needs to be fed into the models and into our data sets at a very fundamental level. So I'll stop there because I could go on, but let's see what others have to say.
Others?
I wanted to pick up on Ian's point on the democratization of technology. I think of research and development investments along sort of, to oversimplify it dramatically, sort of two ends of a spectrum. And one of them, you can think about the breakthroughs that make the impossible possible. And those are, unbelievably inspiring and necessary. But there's the other one, which makes the possible available, right? And that is the point on, Ian touched on, making the technology available to a broader set of developers, for example. But we should think also at the broader set of humans, of people across the planet. And I find that often we don't get as excited about that second sort of investments of innovations, which are the things that make something cheaper and cheaper and cheaper and more easily, more easily manufacturable, or using materials that are more easily sourced. And I worked for a while in Google Maps, for example, and I could see that happening around 2018. We had mapped most of the developed world to a degree that was very useful for local communities to find their local shops and to be able to advertise their products in local searches and things of that kind. But we couldn't afford to map Africa. And then, we began working on automating and simplifying and optimizing the way we build very accurate maps. And around 2018, we began with this experiment mapping the Greater Lagos area. Lagos is about as big as Australia in terms of number of people and complexity, by the way, the Greater Lagos metropolitan area. We were able to map Lagos with 1/80th of the cost that we had mapped all of Australia just a few years before. And now we're well on the way to be able to offer useful digital maps to all of Africa. So just as sort of just one example, that is innovation as well, and that happens deliberately through investment on making things more accessible.
That's great. Anybody else?
Just an anecdote from, I think, the last panel I was on for NITRD a few years ago was there was a discussion about cell phones and how, cell phones are like, as powerful as supercomputers. But if you actually looked at it, I mean, imagine what it would be like to say, well, I've got my own personal Cray 1 and it weighs a ton. You're not going anywhere with that thing. So it doesn't come with you on the airplane or anything like that. I mean, it is about form factor and weight and cost and all of those things. And I think, but the other thing that I have been thinking about recently is that over the years in my career, I've often been in a situation where you're going to a group of, say, domain scientists and say, what would you do with a petascale computer? What would you do with a terascale computer? And you're asking them 10 years before it's built. And so it's very hard for people to think, say, a factor of 1,000 ahead. What would you do with an exascale computer when we've, at each sort of major stage? But I also think now, in some sense, the opposite has happened, which especially as computer scientists, we're so used to the idea of kind of Moore's law broadly and all of the benefits that that's going to give us, that we can just keep thinking of really amazing things that we can do and assume that the computing will be there, that the computing, computing is free. Well, it's actually not free. I mean, it's much cheaper than it was, thousands of times cheaper than it was a decade or two ago, but it's I think that question of, well, what happens when we don't have that sort of hardware sort of accelerator beneath us is, kind of beneath all the other innovations that we want to make at the application level is something that we really need to think about. And what we need to do is, of course, keep that going some way, probably through architectures and maybe alternatives to traditional transistor technology and maybe quantum and all of these different things. But we need to, that's where I think NITRD needs to make the advanced R&D investment so that we can keep all different levels of the stack going.
Yeah, Timothy?
I just want to make a very brief comment, basically echoing my friend Mark Hill. When he said before, it's not really the question about what can we build, but what should we build? And so that question is now more complex because now you need to factor in a number of things, who, why, where, what. And so taking into ethics, taking into accessibility, taking into account the impact of what we will try to build. I'm a firm believer that if you provide enough funding to something, give enough money to anything, you can make something happen. You can build something. You can create something. We're very creative people. We're innovators. We can get some kind of product out of it. So the question is, if you're going to have this money, how best to invest it in ways in which we should. In ways in which we should, the infrastructure, the capabilities, the runway for the future is the way it should be, as opposed to what it could be. And so I think that's a very important thing to keep in mind.
Thank you. Yeah, I'll just mention one final point. I've been involved in responsible AI, which is an investment Microsoft has made in trying to understand and be responsible in the application of AI. And I think the broader issue is that we're talking about the responsible application of all computing technology. It's not just AI. I think AI has raised our awareness of how powerful our technology has become and how it affects way beyond what we think of as the normal consumers of our technology. And so this notion of responsible computing and highlighting that as a pillar of our investment, I think is an important thing going forward. With that, I think we're going to have to stop the conversation. I'm going to give each of you a chance to say one final comment, and then we'll open up the mics for the audience. So why don't we start with you, Luis? Is that okay? We'll go down the row.
Well, first of all, I think that I'm looking forward to meeting more of you. I think that conversations such as these, in which we talk about technology as a portfolio, are incredibly important. To Timothy's point on investment, those are difficult decisions. In computer science, in general, I feel like we are following other fields in which coordination of the work that we do is pivotal. Because it's no longer an individual sport. The Hadron Collider, right, does not put together by 10 physicists. And we are at that point yet. So what's going to define, I think, our success will be increasingly so the quality of our coordination, because the kinds of scale and the complexity of the problems that we're tackling are exploding, right? And also exploding in importance.
Thanks. Ian?
I was thinking a wise man whose name I forget said, that people always overestimate the short-term impact of change, but then underestimate, or in fact can't imagine, the long-term impact. So we all need to be thinking hard, what are the long-term impacts that we should be preparing for, and how can we best make them beneficial to people?
Thanks.
I've said this before in various different forums, but I think it's worth repeating because it's I feel very strongly about this, that in order for us to create the best solutions to whatever problem, whatever domain, whether it's energy efficient and sustainable computing at scale or in any other domain, it requires us to include diverse perspectives, and that's the best way of getting to the best sets of problems. So that brings to mind the importance of diversity, equity, and inclusion in all that we do, in particular to NITRD agencies and those who receive funding from through NITRD initiatives, that we act responsibly in coming up with the best solutions, which by definition, excellence is enhanced by diversity. And we need to think about ethics and justice and equality and accessibility in the kind of solutions that we do. But that comes from having a diverse perspective. So that will help us to, I think, create solutions that are speak to all of humanity and will improve our society at large.
Thank you. Yeah.
Well, I'm going to sort of repeat a little bit about what Tim said, but also pick up on something Ian said earlier, which is, NITRD's amazing success in helping to foster interdisciplinary team science and computational science broadly, and computational, applications of computation to biology and physics and chemistry and many other disciplines. But now we need to think more broadly about what it means to have an interdisciplinary team. So it's not just a domain scientist and an applied mathematician and a computer scientist, and maybe both the software person and the hardware person, which we're going to need because now there's specialized architecture. But to think about what it means to have in that team somebody who's thinking about ethics, somebody who's thinking about social impacts more broadly, somebody who's thinking about economics and other sort of factors or legal issues. And I mean, I think things have not caught up in the legal system with where the technology is at. And I think this community also has some responsibility, even though we're not lawyers, to help to make sure that the knowledge about what the technology can do and how it should be used and maybe should not be used can be shared with people who are experts on law and public policy and things like that. So I think we need to think more broadly about how we educate people in the computing disciplines broadly, and then also how we form research teams. It's not an easy answer, right? I think this is why we all somewhat punted on your last question, because it's hard, and we all recognize, I think, that it's very powerful technology, and it can be used for very amazingly good and helpful things, and it can also be used in ways in which we would rather not, that are actually dangerous. And so I think we do best we can think of, I think right now as a group, sort of what we've said is we need to have teams of people that are going to think about all of those positive and negative aspects.
Great, thank you for those remarks. And I think at this point we're ready to entertain questions from the audience. So please, if you have questions for the panelists, please come up. There are several microphones here. And introduce yourself.
Mark Hill, University of Wisconsin Emeritus and Microsoft Azure. Thanks for the shout out, Timothy. This has been touched on before, but IT companies are investing a tremendous amount of money in moving the technology forward. So what principles should NITRD, academia, government labs, et cetera, use so that their investments complement, or at least certainly don't duplicate, what companies are doing?
I'll say just one brief thing. Invest in crazier stuff, crazier ideas. Invest in things that have, is somewhere else in the risk-reward spectrum that has, amazing reward but remarkable risk. Companies, even companies like Google, which I like to think that are quite aggressive in investing on rather crazy things, will tend to be a little bit more conservative on return on investment.
I would add to that and say invest in things that don't have a commercial payoff that's at least observable right now, because many things that fundamental scientific discoveries may lead to really important societal benefits in the long term or even commercializable technology. But I think NITRD needs to invest in things that are going to lead to advances in human understanding and discovery, and that's and some of that is going to happen in industry too, maybe in certain areas, but things like the Large Hadron Collider is a good example, and the cost of computing on that data, I can tell you, has gone up tremendously when they upgraded that. In fact, some of these scientific projects have underestimated their computing costs by like $1 billion because of the expectation that Moore's law and the price advantages of it were continuing. So I think, NITRD should invest in basic science too, and computing for that.
Visionary, pioneering, high risk, high payoff, potentially high risk, high payoff kinds of investments with partners from industry and of course governments funding it. So there needs to be some investment in terms of the reason why this is being funded. So those are the kinds of things, Mark, that I think, NITRD should be investing in, those high risk, high payoffs things, bolstered by hopefully companies having interest in seeing a value if it pays off, right? And so there should be this coordination between, I think, private, public, government, and academia that will help set a path forward that's profitable for all.
Thanks everyone for the great panel. So this is kind of a big picture question, but how do we convince Congress?
Could you introduce yourself first?
I'm Stephen McLear. I'm at CMU. I'm a CI fellow, postdoc. How do we convince Congress and the public of the need to increase overall investment in computing?
I think we need to be better communicators in our field. I think we're terrible storytellers. I think it's very difficult for people to care about what we do if we just talk to each other. I think we need to invest more in public, communicating with the general public.
Storytellers, that's a great word, yeah. Right.
Right, and what's the story? The story is that these investments pay off. What we were talking about and what was said before, in terms of the actual impact to society and to public good that have come from prior investments and that will come from current investments. And so the storytelling is about, this is actually impactful. This is a good use of your money.
I think there is an understanding of it in Congress in certain ways, but I think it can get oversimplified. And if you look at something like the CHIPS Act, there's really important ideas of investing in the semiconductor industry. But the fact that there's need for investments up and down the stack, I think some of those things we need to better explain.
Jim Wogenbush. I direct research computing at the University of Minnesota, and I'm also the vice chair of CAST, Coalition for Academic Scientific Computing. Thank you so much for your responses to the questions and your insights. I'm going to move a little bit to the softer side of things, but I think equally daunting, if not even sometimes more daunting, and that is really doing things that encourage equity and diversity in our field. You've been in this field for a long time. I would like perhaps each of you to point to a program or perhaps a vision of a program or an idea or an event. Think outside of the box that really made a difference and where you would like to see perhaps future investment in something like that to encourage greater diversity in our field. Thank you.
Well, so there's probably a number of things that could be looked at. I know the NSF has the CEOS, Committee for Equal Opportunity in Science and Engineering. I think this, and there's biennial reports that are made, which talk about, which gives recommendations for how to further diversify computing. And one of the recommendations from that came a program at NSF. This is after I had left already, but they includes program. So that's funding to directed at trying to help diversify, in some ways, computing. But there's a number of things that people, efforts that are done. Well, let me just stop there. So there's funding that's being done. There's efforts that people can do on their own, whether it's mentoring workshops, specifically for trying to increase the pipeline, and the people going from graduate students to the professoriate, which I participate in, a number of different kind of activities like that are available and that exist, that many of us probably have participated in.
So, go ahead. I just say it's, first of all, a wonderful question. I'm going to adopt that as a model for future questions, to put the panelists on the spot, which I think is great. So, I mean, I believe that to diversify computing, we've got to get kids early, before they go to university. And so how do you do that? I don't have any silver bullets, but two programs that I really admired and had some involvement in Chicago, both actually run by two wonderful women at the University of Chicago, Stacy Lindau and Liz Moyer, both aim to get local students out mapping resources in their neighborhoods and then studying what those maps told them and others about various issues of equity or inequity, and to hear these students then articulate what they learned about the power of data and data analysis has been really exciting, and I think it has made a difference in how they think about what they're going to do once they finish their high school studies.
I was going to mention briefly two things. Changing the tone and setting a very high bar for respect in the workplace and civility makes a huge difference. A lot of people are excluded from our field because they happen not to be as abrasive as some of us are. And that really makes a big difference. The other one, if you happen to be somebody who identifies with some of the underrepresented groups, speak up and be more visible. I've been shy for decades about being involved with the Latino groups, for example. And for the last 8 years, I've changed that posture because role modeling apparently is important. I've been taught. And that has been really satisfying to me, and I believe it has helped.
Plus one to what you just said, but I also wanted to add, I think we need to think about sort of reorganizing the pipelines that exist at all different levels. So, when I was, if you look at the computer science departments and who you hire from, it's a very small set of schools. And if you look at the graduate programs and where we admit students from. It's, with some exceptions, a pretty small set of schools. And one of the programs that we had at Lawrence Berkeley Lab, started by David Brown and others, was to bring in community college students to the lab to give them an experience of what it's like to do research. So these are, 2-year college students who can then switch into, say, a University of California system. We need to allow people to have other paths. We sort of think of the traditional paths through the program as the only path. We need to allow people to make decisions later in their career that they might want to come into the field.
Right. And this will be our final question because we're running over. Thank you.
Okay. Katie Seek from Indiana University. So I want to kind of piggyback on that question and move up the pipeline some. And so you're talking about how NITRD helped with the training to do the computing that we're benefiting from today. How do you see NITRD's role in helping us continue to train the pipeline, but balance between the needs of industry and the needs of academia and national labs, so that we can train people without losing our faculty to more innovative and lucrative positions?
Yes, how do we address the salary gaps, I guess. So, I worry about this all the time in various roles, and it is a problem. I think that what we look at in the national labs and we look at in academia is other aspects of the job that bring people to those disciplines. I do think that we have to worry about making those jobs attractive, allowing people, first of all, giving them, for example, sustainable research funding, not saying you guarantee funding, but that people shouldn't be spending so much of their time fighting for small amounts of funding that in order to put together a whole research group. And so when you add that on to the salary differential, I think it can make it harder for people to stay in an academic environment or in a national lab environment where you're soft money funded. So I think that we do need to have a little bit more sort of security in research, or predictability maybe is a better word, in terms of research funding. And then going back to one of the answers to the earlier questions, working on wild and crazy problems that you don't get to work on in industry because they don't have an immediate commercial impact, or they, but they're, really cool scientific problems or whatever.
Okay.
Yeah. So I'll just say one thing. So I'm a co-founder of the CRA Industry Committee, and one of the purposes for that committee, I'm co-founder with Vivek Sarkar, and one of the purposes of that committee is to actually bring computing research from industry, individuals from industry, to the table and to talk about issues that are of importance that cross the boundary between academia, industry, and government. And so I think it's a great question, and I think these conversations have to continue. And I do think we need to evolve. I don't think that we can just stay with exactly how things have been, but how we move forward is going to be very important to think about. So with that, I'm going to say thank you to the panel. It was a really enlightening discussion. I'm so happy that you were able to join us. And and I look forward to the rest of this incredible celebration of the other panels. And thank you to the audience as well. So.